In section 2.3, we're going to look at linear equations. We've seen a linear first-order differential equation previously. They'd be a differential equation of the form some function of x times dy dx plus some function of x times y equals to g of x. Again, this is a linear equation in the variable y because y has coefficients that are simply involving x terms, and it's first order because the highest derivative order with respect to x is the first derivative right here. In this section, we're going to learn how to solve these first order linear ODEs, and oftentimes in order to do so, we want to write it in what's called standard form. And the standard form of a first order linear ODE simply says you want the dy dx and the y term on the same side. Any f of x term should be on the right hand side, and you want the dy dx to have a coefficient of 1. This can be easily obtained from above. To get the coefficient of dy dx to be equal to 1, all you would want to do is divide by whatever factor is out in front here, and then that would kind of go ahead and do it for us. So if we have the following, so if you started with, let's say, a0 dy dx, and this is a a0 is a function of x, plus a1 of x times y equals some function of x, let's call it f of x, all we would really do is divide by that a sub 0. And then this would cancel, and so what we're going to be left with is the following. Dy dx plus, this is still, if you look at this coefficient of y, it's still some function of x. We're going to call it p of x in this chapter, and then this thing is just some function of x. I think they might have called it g or f originally, but we'll call it f of x. It's not the same f we'd see here, but it's still going to be some function of x on the right-hand side. And this is going to be standard form for us. Again, the dy dx term and the y on the same side, and you want that derivative to have a coefficient of 1. Okay. For example, these three equations would be first order linear differential equations. This one here we have dy dx plus 2xy equals to 0. In this one, the 2x would be playing the role of the p of x function, and the 0 would be playing the role of the f of x. Here, for this example, it's really not in standard form because we should have the y on the other side. So if I were to take that middle equation, if I subtract y from both sides, then that would give us dy dx minus y equals to 5. And now it would be in the standard form. P of x, which is the coefficient of x, would simply be negative 1, and f of x would be whatever function on the right hand side we have. That would be equal to 5. This one here is also in standard form already for us, thankfully. We have a 1 dy dx plus y equals to x. Here p of x would simply be the function 1, and f of x would be the function x. Of these three first order linear ODEs, one of the things that we could take notice is that this one and this one are separable. So you could actually solve 1 and 2 via the separable methods we learned in section 2.2. However, this last one is not separable in variables, and so we would not be able to solve it so far with anything that we've learned in the class. What we're going to do is develop a method that will allow us to solve any first order linear differential equation. And that's what we're going to do next. The basic idea behind this is we want to kind of get the left-hand side of this equation, of our standard form, to look like a exact derivative. So we want it to essentially to look like the derivative of some function such that we can then go ahead and integrate it to get the function back and get it back by itself. So what we're going to do in the beginning, let's suppose that there's some function, let's call it mu of x. And let's suppose that our left-hand side can be written as the total derivative, or the exact derivative of mu of x times y. Okay. So let's see what that would mean. So the goal here, and this is what we want to write dy dx plus p of xy. We're hoping that we can write it as the total derivative of some function mu of x times y, where mu of x, we have no idea what it is. Okay, it's some special function. We hope it exists, but let's see what that would look like. Using the product rule here, the derivative of this thing would be the following. It's going to be the derivative of mu. Let me call that d mu dx times y, plus, now we're going to leave the mu term alone. We have mu of x times the derivative of y, which would be dy dx. And now we're going to go ahead and kind of compare what we have. Okay. So what we're hoping for, if we kind of compare these, is we would like for it to be the case that the coefficient we have on our y term should be something like mu times p. Because if we multiply this left-hand side, by the way, so we're multiplying left-hand side, I didn't show that. Let me bring that back up. So if I were to multiply this left-hand side by mu, which is really what we were doing first, this is what we're hoping for it to kind of look like. So we want mu times dy dx plus mu times p of xy to be equal to this right-hand side. Well, these two terms are exactly the same, so those two already match up. What we would also need to happen is we would need for this term and this term to be oops, sorry, I got switched. This term and this term, these are our two derivative terms with respect to y with respect to x. Those are already the same on both sides. What we would now need is for these two things to be equal. In other words, we need for mu times p of xy to be equal to d mu dx times y. These we can think of as both being some function of x times y, so we would need those kind of like coefficient functions to be equal. And that implies that we need mu times p of x to be equal to d mu dx. And this gives us an expression where we should be able to go ahead and solve it for mu. This is going to be a separable ODE. We can multiply both sides by dx first. We can then go ahead and divide by mu. That cancels. And so we get the following. We have p of x dx is equal to d mu over mu. And now we're going to integrate. The left-hand side, we don't really kind of know the exact expression for p, so we can't explicitly do this left-hand derivative, but we know that when we integrated it, we would end up getting some constant of integration. And on the right-hand side, the antiderivative of 1 over mu d mu would be the natural log of the absolute value of mu. So we're almost there. We're trying to solve for this special function. The next step would be that we can go ahead and take e to both sides. It's going to be e to the ln, the absolute value of u. E and the ln cancel, so we get the absolute value of mu equals on this side, we can do something with the constant. We can break it apart, as you've seen a bunch of times. Make this times e to the c, where this is again going to be some constant. So I'm just going to relabel it as keeping it c. E to the integral of p of x dx is equal to the absolute value of mu. We know that that means that mu itself that means that mu is going to be equal to plus or minus c e to the antiderivative of p of x dx. And again, you can just kind of incorporate and absorb that plus and minus into the constant c. E to the integral of p of x dx. And one of the things that's in the homework that's kind of discussed is that this will work for any constant c. So out of convenience, we're going to pick c to be equal to 1, because it just makes our life a little bit easier. Okay. And so that gives us this function mu. And this function mu has a specific name. It's called an integrating factor. So in your notes, star this, highlight this. This is going to be the absolute key and the essence to being able to solve these equations in section 2.3. So the technique is, again, so where is this function mu coming from? It's e raised to the integral of, or I should say antiderivative of p of x dx. Recall that when we had our original ODE, that p of x was that first kind of constant function, not constant function, the function of x that was in front of the y term. So what this is telling us is the following. So let's go back for a moment here. So here's how we're going to end up solving these things. So I have my first order linear ODE. Let's call it dy dx plus p of xy equals, let's say, to f of x. What we are then going to do is we're going to take this entire equation and we're going to multiply it by this integrating factor mu. So I'm going to multiply every single thing by u on both sides. I'm going to multiply e to the negative p of x dx. See if I can squeeze it in here. E to the integral of p of x dx. And I also have to multiply the right-hand side. We'll call it e to the integral of p of x dx times f of x. And now the beauty of this, from what we saw up above, that left-hand side now becomes an exact derivative. That is simply going to be the derivative, d dx, of e to the integral of p of x dx times y. And this is equal to e to the integral of p of x dx f of x. So in essence, all we will now need to do at this step is we're going to need to integrate both sides with respect to x. And that will get our function y, the function we were looking for, our solution. That will then remove it from this derivative, and we'll be able to algebraically solve for y. Okay. So I'm now going to integrate both sides with respect to x. Integrate both sides with respect to x. On the left-hand side, from the fundamental theorem of calculus, the integral and the antiderivative cancel, and so we get the following. We get the e to the integral of p of x dx times our function y. will be equal to whatever this right-hand antiderivative is. 99% of the time, or maybe 90% of the time, we'll actually work with functions where we'll end up with a form on this right-hand side where we will be able to explicitly solve it. So this will be some explicit function that more often than not we'll be able to actually work out old school style and find a classical antiderivative for. And then all you would need to do is divide both sides by this factor in front of the y to get the solution. Okay. And the book actually takes it one step further. They go through the last step and they show what it would look like. If you're just dividing by this factor, it's really the same thing as, ending up with a division on the right-hand side, but then you would also have kind of a negative exponent, okay? So this is the solution. And if you look at it as a formula, it looks absolutely horrible and dreadful. Don't memorize this. This is even what they say in the textbook. Don't memorize it. Instead, go through the procedure each time. When you get a specific linear ODE, more often than not, we're going to be working with functions where, in this class, in the elementary class, where the p of x function is not going to be too horrible, so the integrating factor shouldn't be too bad, and a lot of these calculations will kind of reduce to antiderivatives and things you can calculate pretty easily, from your background calculus knowledge. But this is the trick. We want to begin by finding the integrating factor. So we want to, as kind of like a separate problem, begin by computing this e to the integral of p of x dx term. So let's go ahead and, first off begin by computing that integrating factor. It's also important that whenever we do that integrating factor, that we do not need a constant in that calculation. So normally we know that when we do an antiderivative, we would get a constant out of this. We do not need to include the constant in that part of the integration. Okay, and that's a homework exercise later to verify that that's true. Once we have this function, then what we're going to do is we're going to multiply both sides of the equation by this integrating factor. So multiply both sides of the equation by the e to the antiderivative of p of x dx function. That'll give us the integrating factor times f of x on the right-hand side. And then the key is to remember that even though you might look at the expression you get on the left-hand side, remember that it's always going to be an exact derivative. And the exact derivative that's going to go inside of a derivative bar is going to be the integrating factor times our solution function y. And that will always, always be the case.